Welcome to the next installment of Advanced Chemistry Lectures. This is the 7th lecture in the series on inorganic and organometallic chemistry. And in addition, this is actually part 2 of the lectures on organometallic catalysis. And so in part 1 of this lecture, I did individual catalytic cycles that feature transition metal centers. And I did really 5 processes. I did the borylation of alkanes, a 2,4 palladium catalyzed Heck reaction, a hydroboration reaction by a rhodium-1 complex. I did alkane dehydrogenation by iridium PCP pincers, and I did an olefin metathesis reaction. And so it's really good to understand those processes, but as a researcher or as a student, you want to be able to solve questions that are asked of you, or even figure out the mechanism of a process you may have discovered in the laboratory. And so at the end of that lecture 6 on organometallic catalysis, the part 1 of this series, I gave these 4 questions here, sort of as, let's call it, homework problems. Could you figure out the mechanism of these individual organometallic processes? And so in this lecture, I'm going to walk through these processes and kind of explain how I kind of figured them out myself, and how what you might be able to try to troubleshoot these processes, because I find that many times in my class, students are just say, I don't even know where to begin. And so I'm going to walk through each individual process, sort of talk about where I begin, and then show how I arrived at the conclusions of these individual catalytic processes. And so this first process is a hydrophosphonation reaction. This is sort of a spin on a organometallic process that was published in JACS over 20 years ago, 27 years ago, really. But on the hydrophosphonation using a platinum 0 catalyst. And so notice that in this reaction, you start with diphenylphosphine. You're adding acrylonitrile in the presence of a platinum catalyst, and you're getting your hydrophosphonation product. And so the first thing you want to look at your starting materials. And so here we have diphenylphosphine. Notice that the proton on diphenylphosphine ends up bound to what was the olefinic position right here. You also have an olefin. And so notice when you have an olefin, usually when you're talking about organometallic process, if you have an olefin, you want to be thinking coordination and insertion. However, notice that we have diphenylphosphine. I'm going to draw its structure here, abbreviated structure. And so diphenylphosphine features a pH bond. Well, a pH bond is on the order of about 80 kcals per mole. And so that's easy enough to break at a transition metal center. Furthermore, notice that our active catalyst is a platinum 0, which means it's D10, 14 electron compound. So it's low coordinate, it's electron rich, it really wants to do oxidative addition. And so that's going to be our first step in this catalytic process, is the oxidative addition of the pH bond to the platinum 0 center. And so if we now start our catalytic process, we start here again with our platinum 0, D10, 14 electron active catalyst. We now have the oxidative addition of a pH bond. Notice that the coordination number of platinum goes up by 2, the oxidation state of platinum goes up by 2, and the overall electron count at platinum goes up by 2. And so we have now a platinum 2, D8, 16 electron compound. Notice also we have this metal hydride. It's a platinum hydride. Well, we also have a 16 electron compound, so that's coordinatively unsaturated. Our olefin can then come in and coordinate to the platinum center, forming a transient 18 electron species that can then undergo a 1,2 insertion. Notice that the 1,2 insertion now puts the hydrogen at the position we want in the final product. We now have a new platinum 2, D8, 16 electron compound. This 16 electron compound now, notice that we could undergo a PC reductive elimination step to regenerate the catalyst and liberate your product. Notice that in reductive elimination, like always, the oxidation state goes down by 2, the coordination number goes down by 2, and the total electron count goes down by 2. And so this is a really plausible mechanism for this catalytic cycle. And in fact, let me walk through it again. You start again with your 14 electron platinum catalyst. The oxidative addition of the pH bond gives you a new platinum 2 D8 16 electron compound. Coordination of the olefin, so you can think of the olefin as coordinating in sort of this fashion. Coordination of the olefin followed by insertion gives you your new platinum 2 D8 16 electron compound. You then get PC reductive elimination to generate your product and regenerate your catalyst. However, there's another mechanism that's possible in this in this process. And so you can again start with pH oxidative addition. And so notice again, if you do the exact same pH oxidative addition to the starting catalyst, you again get a platinum 2 D8 16 electron compound. Again, we are coordinatively unsaturated, and so the olefin can bind. However, in this case, notice that the olefin now coordinates and inserts in a 2-1 fashion into the platinum P bond. And so notice that the olefin ends up in between the platinum phosphorus bond, and you get a new platinum 2 D8 16 electron compound. This 16 electron compound can now undergo what is CH reductive elimination. When it undergoes CH reductive elimination, you regenerate your active catalyst and form your hydrophosphonation product. And in fact, this process is exactly how this catalytic cycle works. You in fact get a pH oxidative addition first, followed by coordination and insertion of acrylonitrile into the platinum P bond. When it coordinates and inserts into the platinum P bond, you get a platinum 2 D8 16 electron compound that undergoes CH reductive elimination to generate your hydrophosphonation product and restart your catalytic cycle. And so in fact, this is how the catalysis occurs. It's in the left-hand corner or the left-hand cycle. And so this was actually investigated again, like I said, back in Jackson, 1997. And so what they were able to show was that this compounds that look like this do not actually undergo PC reductive elimination. So it is more likely that the catalytic process is occurring by the cycle on the left. And in fact, both, though, are totally reasonable answers. And so if you were given this on an examination, I'm sure that both answers would be appropriate. It would be a little bit unexpected, actually, for this left cycle to be operative, but that is, in fact, the case. This is how platinum catalyzed hydrophosphonation occurs. All right, and so we're done with one of the 4 examples here. And so now we're going to go to the ethanolysis example. And so ethanolysis, we talked about back in a couple different times in a series of lectures, first on olefin metathesis. We also did a olefin metathesis reaction in the part 1 of this lecture on organometallic catalysis. But now we're going to do an ethanolysis reaction. Well, an ethanolysis reaction involves taking a longer chain olefin, in this case a C8 olefin. On reaction with ethylene, the C2 fragment, you get a C4 product and a C6 product. And so how is this going to occur? Well, I tell you that the active catalyst is this molymethylidine. And so we're going to start with that. I've abbreviated our molymethylidine now as just MCH2. And the reason for that is it makes it easier to draw the metallocycles. But again, the metal center can be moly or a tungsten. And so step 1 is to form metallocycle butanes anytime you have an olefin metathesis reaction. And so notice again, we start with our C8 product here, C8 starting material, excuse me. We are now going to form a metallocycle butane. Notice that these 2 carbons are going to be part of the metallocycle butane. And so when that initial metallocycle butane forms, notice again, here's 1, 2, 3, 4, 5, 6, 7, 8. This carbon is the same as the methylidine carbon. If you now open up in the productive direction, you notice that you liberate 1 hexene. So here's 1, 2, 3, 4, 5, 6. That's your 1 hexene product, the C6 fragment that is observed in the ethanolysis reaction. Notice you form a new alkylidine, a 3-carbon alkylidine. Now in the process, in the presence of ethylene, so these reactions are run under a high pressure of ethylene, so you have ethylene everywhere. You form a new metallocycle butane. Here is your 2 carbons of your ethylene. They are in these 2 positions in your metallocycle butane. You open in the productive direction again. Notice that will give you a 1, 2, 3, 4 carbon olefin, the 1 butene, which is the other C4 product. You then reform your methylidine. Your methylidine reacts again with the 8-carbon starting material olefin, form a new metallocyclobutane, the exact same one you formed at the very beginning of the catalytic process. This goes round and round, and you get your ethanolysis product. So notice that you start with a C8 and a C2, and you end up with a C4 and a C6. You start with 10 carbons, you end up with 10 carbons, and this is key in olefin metathesis. Remember, olefin metathesis reactions, never panic. As long as you do not add or delete carbon atoms in any random fashion, you cannot be wrong. If you open your metallocycles in the wrong fashion, you're just going in the opposite direction on the equilibrium arrow. Take your time, think, make sure you go in the productive direction. But if you do not, don't panic. Just don't delete carbon atoms or add carbon atoms, and you eventually get on track and form your products. In this case, we started with C8 in the presence of also C2 ethylene. We form C6, 1-hexene, and C4, 1-butene. This is how this ethanolysis reaction occurs. All right, so we've done 2 of them now. We've done hydrophosphonation and we've done ethanolysis. Let's now work on this Buchwald-Hartwig reaction. And so the Buchwald-Hartwig reaction usually makes anilines. However, sometimes the following side products are formed. How? And so I think we should start by doing the general or the usual or the kind of accepted most basic mechanism for the Buchwald-Hartwig cross-coupling. So notice that we start with a palladium 0 catalyst. This is our active catalyst. If N equals 1, and N can equal 1, you get a fleeting intermediate. But if N equals 1, this is very commonly encountered when you start with a Buchwald ligand. A Buchwald ligand is a biaryl dialkyl phosphine, and so they take this general form. Often you have substitution at the top ring, and you can also have substitution pattern on the bottom ring. Maybe these should be double primes. These should be actually primes. And so this is a Buchwald ligand, and so a Buchwald ligand will promote low-coordinate electron-rich transition metal compounds. And so if we start with our active catalyst again right here, if N equals 1, we have a palladium 0, D10. If it's ligated by a Buchwald ligand, that would be a 12-electron compound. The first step is the oxidative addition of an aryl halide. In this case, I've drawn it as aryl iodide. You then get a palladium 2, D8, 10, 12, 14-electron compound. That 14-electron compound can now coordinate an amine. When it coordinates an amine, we now have a 16-electron palladium 2 D8 compound. Deprotonation followed by salt metathesis will now notice that you can deprotonate the NH bond. It's most easy, I think, to see it in this fashion, like so. If that occurs, that is now a deprotonation followed by salt metathesis. You would get the palladium amido shown here. This is a palladium 2 D8 14-electron compound. This 14-electron compound can then go under CN reductive elimination, generating your aniline product, your aryl amination product, and restarting your catalytic cycle. Okay, so let's walk through that one more time. Again, the first step is oxidative addition of aryl iodide. This gives you a palladium 2 D8 14-electron compound. Coordination of the nitrogen starting material will now give you a 16-electron intermediate. Deprotonation followed by salt metathesis will now generate a new 14-electron compound. The deprotonation, again, you have a strong base, sodium terpetoxide. It will pluck off the hydrogen. You can then think of it going in this fashion to give you the 14-electron compound shown here. Notice also, if we think about it in terms of salt metathesis, once it's deprotonated, you can kind of draw it like so. Remember that there's a sodium there hanging out, and so what we can do is kind of draw a dotted line intermediate. Boom, boom. If you do that, you can see how sodium iodide would be liberated. You now have a new platinum amido, potentially with some double bond character, but that you can think of this now as your deprotonation and salt metathesis step. Notice that 2 and 3 together, this kind of step here, is the equivalent of transmetallation that we saw in most other palladium catalyzed cross couplings. In those processes, the final step here in which you liberate your product is CC reductive elimination. Here it is CN reductive elimination. The CN reductive elimination takes your palladium 2, D8, 14 electron compound. Notice the reductive elimination step. The coordination number goes down by 2. The oxidation state goes down by 2, and the total electron count goes down by 2. You have a 12 electron active catalyst in this case. This is the general mechanism for the Buchwald-Hartwig cross-coupling. And so the question, though, asked, remember, how do you actually form these other byproducts? And so this is what we got to focus on in this question. And so I've kind of given you the hint already, if you paid very close attention. This intermediate over here, notice I've already drawn you your beta hydrogen. Well, in this case, you have a beta hydrogen in this position. That is the beta carbon atom. So beta hydride elimination will now liberate your imine. When your imine forms via beta hydride elimination, so this again is beta hydride elimination. Notice that you have a new platinum 2, D8, 14 electron palladium hydride. This palladium hydride can now undergo CH reductive elimination. When it undergoes CH reductive elimination, you liberate your product, you restart your catalytic cycle. And so the formation of these products in the box are actually formed via the first 3 steps of the same: oxidative addition of the aryl halide, nitrogen coordination followed by deprotonation and salt metathesis. You now end up with this intermediate that has a beta hydrogen. You get beta hydride elimination. Beta hydride elimination followed by CH reductive elimination at palladium will generate your palladium 0 starting material or active catalyst, and round you go. All right, and so we did this one. How about this process shown here? All right, mechanistically show how the dual catalytic process is possible. For simplicity, use a tungsten methylidine, so this as your active catalyst, and your iridium dihydride is the other active catalyst. And so if you go back to lecture 1-6, we talked about both of these catalysts. The iridium PCP compound is used for the dehydrogenation of alkanes, while the tungsten methylidine is used for olefin metathesis. And so how does this process occur? Well, this process occurs, we're going to start with the iridium dihydride. Well, the iridium dihydride, we know that the active species is really this iridium 1 D8 14 electron fragment. And so how do we get there? Well, what we must do first is lose an equivalent of dihydrogen. That dihydrogen can be lost in a couple of different ways. You can add a sacrificial olefin like tert-butyl ethylene, which looks like that. We talked about that. You can also, if you're under a flow of argon gas at high temperature, which this reaction is, you can actually eliminate H2 from the starting iridium 3 D6 16 electron compound. Notice that this is a reductive elimination. If it's just drawn like this, the oxidation state of iridium went down by 2, the coordination number went down by 2, and the total electron count went down by 2. And so when you get your iridium 1 D8 14 electron fragment, it can undergo CH oxidative addition in the first step, either to ethylbenzene, which is shown here, or any old alkane, which is shown here. Notice that what you get then is iridium 3 D6 16 electron compound. Both these 16 electron compounds have beta hydrogens. You can then undergo beta hydride elimination. Beta hydride elimination. When that occurs, you now generate new olefins. These are, again, notice that this is the dehydrogenation step. And so you get your 2 new olefins. Well, if you have 2 new olefins and you have an olefin metathesis catalyst, what can occur is they can enter a cycle for olefin cross metathesis. We now again have a methylidine. Well, that methylidine can now form a metallocyclobutane with the terminal olefin product. Notice that if we now open this up, if you open this up in this direction, you will now lose ethylene as one of your products. You form a new alkylidine. That new alkylidine can form a new metallocyclobutane. If this opens in the productive direction, we'll reform our methylidine, liberate our second olefin. Notice now we have 2 new olefins. But if you look at the products are in fact hydrogenated. But notice that when you formed the initial olefins, which I put a check mark next to, you reformed your iridium dihydride. Well, that iridium dihydride can now hydrogenate those 2 newly formed olefins, this one and this one. I'm showing it for this one. Well, here, now we get a coordination and insertion. And so you started with an iridium 3, D6, 16 electron compound. The coordination of the dye-substituted olefin would transiently give you an 18 electron compound. You then get insertion into the iridium H bond. You now have a new iridium 3, D6, 16 electron compound. You can get CH, reductive elimination. If you get CH, reductive elimination, you generate your products. When your products forms, notice that you again form this compound right here, this iridium 1, D8, 14 electron fragment, which can now re-react with alkanes. When it re-reacts with alkanes, you now restart your catalytic cycle, and round you go. And so this really is a extremely impressive product. You know, it is, in the question, a dual catalytic process, but there is really two catalysts, the iridium PCP pincers, that are doing two different reactions. They're doing both dehydrogenation and hydrogenation, while the olefin metathesis catalyst, the tungsten methylidine, is doing olefin cross metathesis. This is how this catalytic process works. It's kind of mind-blowing. Maybe your brain just blew a little bit, but don't worry. If it did, just take a breath, go back and look at all the individual steps. The individual steps are not that complicated. You just have oxidative addition followed by beta hydride elimination. You have olefin metathesis, and then you have olefin coordination and insertion and reductive elimination. All the processes we've already talked about individually. You just got to put them all together. And so we've now done all four of these catalytic reactions. I hope you arrived at similar conclusions I did, and I will post shortly the next upcoming lectures. They're going to be on hard-soft acid-base theory, the iso-Lobel analogy, and probably some on the coordination geometries, including the ligands. And so I hope you learned something, and stay tuned for the next lectures.